Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, welcome back. We've got two great talks. The first talk is on sampling from probabilistic submodular models. It's by Alkis Gotevers, Hamid Hassani, and Andreas Kraus. And Alkis is going to be giving the talk. Thanks.
Okay, thank you. Hi, everyone. So my name is Alkis Gotevers, and I'm going to talk about sampling from probabilistic submodular models. So this is joint work with Hamid Hassani and Andreas Krause at ETH Zurich. So first, I want to motivate these kinds of models. So let me start with an example application. So imagine you have a big collection of images, and you want to summarize it. So you want to select a few representative images from this collection. One objective that has been used for this task is facility location. And I want to go through this in detail here, but on a high level, it encourages a combination of covering the image collection as well as having a diverse summary. So if you call the set of images V, then for any summary, so for any subset S of V, this function would give you a score f of s. Now, interestingly, if you look at adding a new image, so the benefit of adding a new image to an existing summary 1 here, and compare this to the benefit of adding the same image to a superset of the original summary, then according to this objective, the first benefit is always greater than the second one. So this intuitive property of diminishing returns is called submodularity. And submodular functions have been used to model notions such as coverage and diversity, while their counterparts, supermodular functions, have been used to model notions such as smoothness and cooperation. And of course, the problem, both problems of minimizing and maximizing submodular functions are extensively studied. However, there's very little existing work on actually defining probabilistic models using submodular and supermodular functions. And here's an example of how that might be helpful. So rather than just optimizing the function and getting one single summary, what you can do if you have a probabilistic model is just sample from this model, get a bunch of summaries, and then let the user select the one that suits his or her needs. So we would like to define probabilistic models using submodular and supermodular functions, but also there are standard probabilistic models that have been used for some tasks in the past. So here's another example application, which is about segmenting an image into foreground and background. So ideally, you would like to get something like this here. So black is background, white is foreground. And because it's really hard, people have been looking at actually using probabilistic models to get the probability of each pixel being assigned to foreground or background. So these yellow and red regions are the uncertain regions about the labeling. And of course, one standard model people have been looking at is just taking the image, constructing a grid of pixels, connecting the neighbors with edges or with pairwise potentials, and then if you call the set of all pixels V, you can get the probability distribution over subsets of foreground pixels, where the probability of a subset S is proportional to e to the sum of all these pairwise potentials. Now, what is interesting to look at is also if you can use some richer information of the image rather than these pairwise potentials to get better results. So one such example of what are called higher order models comes from, for example, using superpixels. So you first acquire these colored regions here, the superpixels, and then if you look at one of them, what you can do is define a higher order potential, fi here, and if you use as phi, say, a convex function, what this encodes is the tendency of all pixels in the superpixel to be assigned the same label. So if all are foreground or all are background, you get a value of phi max, otherwise you get much lower value. And using this, then, you can define a new distribution, which is proportional to e to the sum of all these superpixel potentials. And for example, from some recent work by Jalong and Krause, you can see that these higher order potentials actually achieve this much crisper probabilistic labeling than pairwise ones. So to summarize my two major points up to now, on the one hand, we would like to go beyond submodular optimization and actually use submodular functions to define probabilistic models. And on the other hand, we would like to take existing probabilistic models and equip them with higher order interactions. So both of these points lead us to consider a class of models that we call probabilistic submodular models, or PSMs for short, and they are distributions over subsets of the ground set. So the probability of a subset S is proportional to e to f of s, where f is a submodular or supermodular function. And z here is just a normalization constant. So let me make a quick connection to Markov random fields, because you're probably all much more familiar with those. So as I said, PSMs are defined to a ground set V of size n. a submodular or supermodular function f, and then we get a distribution over subsets. So you can see the same thing equivalently as an MRF by defining a binary random vector x of length n, and then you have a set of factors phi I, each of them with scope ci. So ci here is the ith clique in the MRF. And then what you get is the distribution over binary vectors, where the probability of a vector x is proportional to e to the sum of all these factors. So when I talk about model order here, what I'm referring to is the maximum clique size of the corresponding MRF. Now let me also quickly show you how this the class of probabilistic submodular models generalize many well-studied models of the past. So I'll start with product distributions here, which are just distributions over independent sets of random variables. Next, we have attractive pairwise MRFs, so for example, Ising models, Potts models, etc., like the segmentation example that I showed you before. Their counterpart are repulsive pairwise MRFs, which encode notions of diversity. Another class of models that have been used to encode diversity are determinantal point processes. And now log-submodular distributions generalize this diversity-inducing part of this model space here. And their counterpart log-supermodular distributions generalize attractive models. So in the end, the union of these two classes we call probabilistic submodular models. Now, of course, what we're interested in doing in these models is inference. So compute various marginal probabilities, say the probability of a pixel being assigned foreground to foreground or background, or conditional probabilities. For example, the probability of an image being included in our summary, given that we have already selected a few images to be in a partial summary. So, of course, people have been doing various kinds of inference in the past, so we know that exact inference is tractable only for limited subclasses, say product distributions, DPPs, tree-structured MRFs, etc., but it's really hard even for simple Ising models. Now, low-order MRFs are also a model class that people have extensively studied, and they've come up with algorithms such as loopy belief propagation, mean field, etc., but all of them are actually exponential in the model order, so they're still not feasible for general PSMs. Now, in last year's NIPS, Jalung and Krause were the first to consider the general class of PSMs and propose a variational approach for inference in this class of models. So what we're asking here is whether the usual alternative to all these deterministic inference methods, which is of course sampling, is feasible for PSMs and what we can say about that. In particular, we're interested in Markov chain Monte Carlo sampling. So as you might already know, the idea here is that we have a state space omega and a transition matrix P with corresponding stationary distribution pi. And what we want to do is define a Markov chain ST that makes local moves according to this transition matrix P. In our case, the state space will be the power set of V, and we will construct the transition matrix so that it corresponds to the Gibbs sampler. And then, of course, the stationary distribution that we're interested here is the PSM distribution. So for a small ground set of size 3 here, this is how our state space would look like. So it's just all subsets of the ground set. And let me quickly show you how the Gibbs sampler would work here. So you start from an arbitrary state as 0, and then let's say you have done t iterations, and you've ended up at state, the singleton state 2 here. So the first step is to select a random element from the ground set. So here we would have 3 choices, either 1, 2, or 3, which correspond to 3 potential transitions that we can make. So say here we select v equals 3. Then the next step is to compute the conditional probability of adding or removing this element to our current set. And the final step is to actually flip a biased coin and make the transition or just stay at the same state as before. So if you look at all possible transitions in the state space, you get just this subset lattice here, according to the Gibbs sampler. And of course, this is also, as I told you before, equivalent to just a binary hypercube of dimension equal to the size of the ground set. Now, of course, what we want to ask about this Markov chain and the local moves that it makes is whether it converges to the stationary distribution. And this is usually measured by looking at the total variation distance between the probability of the Markov chain and the stationary distribution. And in particular, we look at the maximum of that over all possible starting states. So it is well known that under some mild assumptions, that is ergodicity, this total variation distance goes to 0 asymptotically. So the more interesting question here is actually how fast does this converge? And this is measured by looking at the mixing time. So this is just the minimum amount of steps that we need to get epsilon close to the stationary distribution. So unfortunately, mixing times for general PSMs are exponential in the size of the ground set. And in particular, they're exponential even for general pairwise models, as was shown by Jerome and Sinclair in '93. So what we're doing in this paper is establish some sufficient conditions that guarantee sub-exponential mixing times of the Gibbs sampler on PSMs. So to get to our first result, I need to show you a couple of definitions first. So we call a set function f modular if this equality here is satisfied for every subset A and B of the ground set. And we call it submodular if the left-hand side is greater, and supermodular if it's the other way around. So now using this, we can look at the amount by which this inequality is violated by a general function f, and just take the maximum of this over all possible subsets A and B. And we call this quantity zeta f here the distance from modularity. Now secondly, you can take any submodular or supermodular function and decompose it into a constant term, a modular term, and a normalized monotone submodular term. And if you look at what this means in terms of the distribution, it just means that the PSM can be written as a factor of a product term and an interaction term, so a term that contains all interactions between elements. Okay, now we can get to our first theorem of the paper, where we use both these things. So what we say here is that for any PSM, which is defined through a submodular or supermodular function f, we get a bound in the mixing time, which is quadratic in the size of the ground set, so we have this n squared term here, but it's exponential in the zeta f, so this distance from modularity. And note here that this f is the lower case, so we just care about the monotone part. Now you might think that if the zeta f actually increases in n, then this exponential term might blow up. And this might be indeed the case for some examples. But there are also many interesting cases where the zeta f is, say, constant in n. So let me get back to our superpixel example here. Remember, we have one potential per superpixel, and then our function is just the sum of all these superpixel potentials. So it's easy to show that in this case, our distance to modularity, so the zeta f, is bounded by L, so the number of superpixels, times phi max, so the amount of smoothness that we're trying to impose. And note here that this L might be around 50, say, for this image here. So if you adjust phi max, you can make this exponential term be fairly small. But if you were to actually see this as an MRF, then you would get model orders that are, say, 10,000 or so. So the clique size would be around 10,000 for the largest superpixel. Now let me also quickly show you a proof outline of our theorem here, just a high-level picture. So we use a method called method of canonical paths, and I'll use here a slightly larger state space of ground set size 4. So the idea is to set up a flow routing problem in this state space graph. So here with different colors, I show the probability of each state according to the PSM distribution. And what we want to do is for every pair of states, we want to route an amount of flow equal to PA times PB from each state A to each other state B. So the first step is to construct what is called a canonical path between each ordered pair of states. So we will use this path then to route flow from A to B. For example, here what we could do is just add or remove elements in numerical order. For example, starting with A, we would add element 1, remove element 2, add element 3, remove element 4, and we are at B. Now imagine doing this for every pair of states in the state space. The second step is to define a capacity of each edge, which will be proportional to the probability of making this transition that the edge corresponds to according to the Gibbs sampler. So here I show this with different widths on the edges. And finally, we can define a quantity called congestion of an edge, which is just the total flow that goes through the edge according to our canonical path construction, divided by the capacity of that edge. So here I show this with different colors. Now, the reason we care about this congestion quantity is because a theorem by Sinclair in 92 shows that you can bound the mixing time of the Gibbs sampler by bounding the maximum congestion among all edges on the state space graph. So what we do in this paper is bound this maximum congestion of a PSM using this quantity, this distance from modularity zeta f. Now let me quickly go through our second theorem, and I don't want to get into detail here, but roughly speaking, this theorem gives us better bounds on the mixing time, but under stricter conditions or under special structure of the PSM. So here we use a different quantity, this gamma f, which we call maximum total influence, and what the theorem says is that if this quantity gamma f is smaller than 1, then we get a mixing time which has a dependence nlogn on the size of the ground set, and there's also this 1 over 1 minus gamma f dependence in front. We also show in the paper a simple way to bound gamma f if the corresponding function f can be decomposed into a sum of simpler functions. Now, for people who are familiar with these concepts, this kind of theorem is closely related to what are called Dobryshin conditions for uniqueness of Gibbs measures, and also closely related to influence matrices and their norms. Furthermore, Rebeschini and Carbassi, in contemporary work to ours, showed a similar theorem, which is not directly comparable, but still has a similar flavor to this theorem here. So finally, let me show you some experimental evaluation. So our goal here is to compare to against the variational approach of Jalonga and Krause from last year. So we use the exact same models that they used in their paper. Two of them are log-supermodular models, and one of them is log-submodular. So here I'll concentrate just on the third model, which is an e to the facility location model. So what we do is compute marginal or conditional probabilities of this form here, where S starts from an empty set and iteratively increases. So we condition on more and more elements. Also, we constrain the ground set size to be at most 20, so that we can actually compute exact marginals and compare to them. So in this plot, I'll show you on the x-axis the percentage of conditioned elements, so the set of the size of the set S, and on the y-axis we have the mean absolute error compared to the exact marginals. So if you look at the two flavors that the variational approach comes in, you see that both of them start with a relatively high error, and as we condition on more and more elements, the error decreases. If you look at just 100 Gibbs iterations, you see that we get a fairly consistent error across all conditioning regimes. And if you increase the number of Gibbs iterations, this error gets lower and lower. So you see that we can beat the variational methods across most conditioning, except if we condition on almost all elements of the ground set. So to sum up, we've looked at the class of models called probabilistic submodular models, which generalize a few well-studied subclasses of the past, and we have shown conditions under which we get fast mixing times of the Gibbs sampler in these models. So we think this gives us a principled way to actually identify higher order classes of models that are amenable to efficient inference. And also, we have the first indications that sub or supermodularity can actually lead to faster mixing times. So for more discussion, please come to our poster number 70. Thanks.
So do we have any questions for Alkis?
So there are other ways of measuring distance from modularity besides your gamma f, and gamma f is hard to compute. And there are things like curvature. Have you actually thought about, for example, other more computable ways of measuring distance from modularity?
So, okay, so first of all, this quantity that we have defined, you might be able to analyze for some cases and actually get some simpler way of computing it. Now, in terms of curvature, it doesn't directly come into these results here because somehow the way we define the probabilistic submodular models give us additive distances from modularity, whereas curvature itself somehow has a division in there, right? And this doesn't come up. If you look at your kind of models that you had actually defined, so the submodular point processes, there you might actually get something that might be related to curvature. So that might be an interesting direction to look at.
Another question? So I actually have a question. The cases that you looked at, you assumed a finite set of indicators, but for some of the examples in your set, for example, determinal point processes, you can have an unbounded number. Have you looked at whether you can construct similar guarantees without a finite state space?
Oh, no. Our whole formulation somehow depends on submodular functions, which are, at least as far as I know, usually defined on finite ground sets. So no, we haven't, at least not yet, looked at this case.
One more question.
Just one quick question. I think I missed something. So what I'd like to understand is, it seems to me that this is very similar to a covering problem in which if I select a node, then I can't select any of its neighbors. And that's like in an Ising model, those are really hard problems to solve. Mm-hmm. So I'm not really sure how you're doing the inference in such a way that you can get anywhere. Because it's like an odd cycle, you know.
Right. Okay. So yes, I agree. They are in general very hard problems, and that's what I meant when I said that in general you get exponential mixing times, right? So what we are looking at is which cases or which subclasses of these models you can actually do efficient inference in. So we want some some theorem that says that if this holds, then you actually get efficient inference. So we're not claiming that for all such models you can get efficient inference, of course. This is very well known to be a very hard problem in general.
Okay, thank you so much.
Sure.
Okay, let's thank Alkes again.
Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.